Hey, welcome back everyone. Steve Buchenroth here. The goal of today on this video is to try to help you understand and be able to teach, whether you're a student or a flight instructor, to understand and teach drag. So we've got total drag that's comprised of both parasite and induced drag. So let's take a look at that. So here's how I start teaching it. This doesn't mean you have to teach it this way, but here's how I do it. So I look at it and I say, look, we've got total drag. Drag total is equal to parasite drag plus induced drag. I for induced drag. Now, if we break parasite drag out separately, well, parasite drag, it is equal to, parasite drag is equal to form drag plus skin friction drag plus interference drag. In fact, I'll just go up here and write out the whole word here on this one, induced drag. All right, so parasite drag plus induced drag equals total drag, and parasite drag equals form drag plus skin friction plus interference drag. So let's kind of break these out and make it easy. First, we're going to start here with parasite drag. So we're going to work on parasite drag, coming on down here, parasite drag, and we're going to start with form drag. Now, form drag has three things that give us form drag. It's the size of the object that the airflow is going over. So it's the size. It's also the shape of the object. And furthermore, it is the speed. Size, shape, and speed. So I'm going to kind of diagram this out the best I can to help people understand it. And we're going to hold the size of the object and the speed constant in this demonstration. So we're going to hold size constant, going to hold speed constant, and we're going to vary the shape. So let's start off with four objects. And I'm going to turn you back to your PHAC, your Pilot's Handbook of Aeronautical Knowledge. And I'm going to tell you, if you go to present one, it's 5-7. But if you go to figure 5-7, chapter 5, on the 7th illustration, you'll see where they depict a flat plate, a sphere with a fairing, and a sphere with an inside housing. But I'm going to simplify that a little bit for us here, and we're going to start off with a flat plate. Call it a brick, call it a flat plate. It doesn't matter. We're going to do it. So we're going to say we got this flat plate right here, and we'll do this. So here's our flat plate, and it's the same dimensional thickness as if we then move to a ball, and so. What's important is we see that each of these objects split the air the same. So now we're going to move from a ball to something more like a wheel pant. So we'll draw this out. We've got a little bit more aerodynamic shape to it. Wheel pant, and now the last one will be a wing. So again, we'll draw this out to look more like a wing, and it's got some distance to it, and that's supposed to represent a wing. Now, I want to drive the point home again, because you need to make sure you do this with your students. You've got to make sure they understand that we're comparing equal size. So the brick is 2 units on the grid. The ball is, so goes the wheel pant, and so is the wing. So we're parting the air the same. So look, we've held the size constant right here. Okay, and we're going to make the speed of the air the same. We varied the shape actually behind the wind, the airflow, in the wind tunnel or in the air. So what happens here, as this air comes over, it hits this brick. It doesn't just come to a stop, it hits this brick right here. And you'll notice it trends out, and it starts doing this, and this one does the same, and then it comes in and does the same here, and this hits it, comes around. So what happens here is this air goes turbulent. The air becomes turbulent, and it takes quite a while for this air to come back together. So inside this thing is just all this turbulent air. Whether it's behind the back door of a semi or whether it's behind a 757, there's turbulence right there. And so what we've got is in that turbulent air, it tends to last for quite a while. Now, on the ball, per se, it comes in, and it makes that corner better. It's smoother. But it still doesn't get back together for a while. But it doesn't carry out nearly as far. You see, if you look at your figure 5-7 in the PHAC, that's what they're showing us. They're showing us that now we're dealing with a sphere that has less turbulence. So hence it goes for a shorter distance. Now we get to the wheel pant. And the wheel pant really doesn't begin to have as much turbulence there. And then, of course, the wing has very little. So because the air is turbulent, the FAA tells us. Now, where they tell us this, they tell us what I'm going to say. It's in the Instrument Flying Handbook. But in the Instrument Flying Handbook of all places, it tells us that turbulence, put this in red, turbulence leads to lower pressure. The T for turbulence. Turbulence leads to lower pressure. And it's the lower pressure from the turbulence that causes the drag. Now, if you talk to engineers, a lot of them will tell you that low pressure causes turbulence, which causes drag. But the FAA tells us that turbulence causes low pressure, which causes drag. Again, that's in the Instrument Flying Handbook. It's actually on page of the current one, page 4-4 in the Instrument Flying Handbook under form drag. Now that number is going to change as these videos grow old. But turbulence, according to the FAA, turbulence causes low pressure and low pressure causes drag. Hence, the more turbulence, the more low pressure, the longer it is, the more drag. So the drag caused from the brick isn't because it's hitting the flat face of the brick. Some of it is, yes, some of it is. But it sent the air into a tizzy for so long, we have a much longer drag vector. Now, the air that hits the ball isn't nearly as far out there. And then, of course, the air that did the wheel pant, well, it's not nearly as much. And you have very, very little off of the wing here. So we held the size constant, we held the speed constant, we varied the shape, and when we varied the shape, you see where we ended up getting the drag from by varying that shape. What we've got here is this shape then, right here, and that is what causes. That's what causes parasite form drag. So we walk through what causes form drag. So that's one of the three elements that causes the overall parasite drag. All right, let's talk about the skin friction drag for parasite drag. So we've covered form drag. Now we're going to talk about skin friction drag. So let's say we have an airplane. We're going to assume this airplane is flying into the screen right here, going away from us. And if we could look down on that wing through a microscope, a high-power microscope, maybe 1500 power, that's the example they use in the Pilot's Handbook of Aeronautical Knowledge when they look at skin friction drag. We could look down on that, and if we could see the ridges, when we would look at the ridges, they look something like this. The top of the wing is mountainous in structure. And that's just the surface, magnified 1,500 times, and you can see how rough that is. And of course, that's what ultimately ends up, causing the air to slow down on the top of the wing and go down to zero and become the boundary layer. But what we've got right here is little bits of air that's caught up in this. And this little bits of air that catches on all these little spots down in here, in that air, that's what's slowing the air down. And that slowing of the air causes the airflow slows down and becomes skin friction drag. It puts a drag on the airplane. Okay, so that's skin friction drag. All right, now the next one that we're going to talk about is interference drag. But I'll go back and recap this real quick. Skin friction drag is a product of two things: the viscosity of the fluid, the thickness of the air. Think water going over a submarine versus air going over a wing. The submarine, the elevator on the submarine is going to be subjected to thousands of times more drag because of the viscosity of the water. So the viscosity of the fluid coupled with the surface friction, that's what causes skin friction drag. Now, our last one is interference drag. What happens where two surfaces come together a lot of times is, if we look at this T-tail, airflow changes direction. There's a 90-degree bend right there. So a lot of times you've got turbulence coming off where it changed directions right there. Or right here you got turbulence coming off places where it changes directions. Or right here. So that is called interference drag. Let's get a little better look at it. Let's just say we could take a look at like two rivers coming together. So if I had a river joining another river, and it looked something like, we'll just say it looked something like this. And these two rivers come together, and I've got air, water in this case, going down this river, and I've got water hitting it right here at this river. Then we can intuitively see that water is going to do turbulence, and then it's going to take a while to straighten out. Maybe after a while it straightens out again. Well, it's that spot that we're talking about. It's that location right there where airflows come together that give us this interference drag. So let's summarize parasite drag. We've got form drag, which is based upon the size, shape, and speed. We held the size and the shape constant, or the size and the speed constant. We varied the shape, and we showed you how turbulence leads to low pressure, and low pressure leads to drag. Secondly, we looked at skin friction drag, and we saw how the air gets caught up, the viscosity in the air gets caught up down in the surface friction areas of the wing, and that then, of course, causes the air to slow down and place a drag on the wing. And last of all, then, is interference drag, where two shapes come together. The air has to meet each other, get together, change directions. So again, we get turbulence, we get low pressure, and that causes drag. So that is, in a nutshell, parasite drag.